All right, so let's talk a bit about like just general bone anatomy. So bone structure here. So here we have something called the epiphysis. So remember, FP can mean outer or above, but now we're talking about what we have here is the epiphysis. So here we have it at the ends. So this is a way I'd like to remember it. Like there's three major terms: epiphysis, metaphysis, and diaphysis. So this is the way I memorized it when I or remembered it when I first studied this. E starts with E, so epiphysis are at the end. So you're not, if in the long bone you just don't have one epiphysis, you actually have two epiphyses right here. So epiphysis, two at the ends. You have two ends to a long bone, epiphyses at the ends. Now you have something called a diaphysis. So this refers to the central part of a long bone. So here's a little flashback to maybe ninth grade geometry. What do you call this line right here? This red line. So you call this red line a diameter, right? So it goes straight through the center. So this is the way I like to think of it. Diaphysis is in the center like a diameter. So that's how I remember where diaphysis is central like a diameter. Now, epiphysis and diaphysis. So you have two epiphyses at the end, a diaphysis in the middle, but you have something where they meet. And this is where you have the metaphysis, where an epiphysis meets an diaphysis. So that's how I memorize where those three broad categories of regions are. So again, epiphyses at the ends, diaphysis in the middle like a diameter, and metaphysis are where the two meet. Now let's talk about just compact versus quarter and spongy bone. So compact, well, spongy sounds like big, airy, and fluffy, right? And compact, that means it's very dense. Compact bone in some textbooks is also called cortical bone. So that's what we have here. So in the long bone, you typically find compact bone along the diaphysis or the middle. So this part, as you can see here, that this part right, the ends are very spongy. You can see all the air pockets. But actually right here, I mean, remember how I said it's kind of hollow in the middle? But at the very edge of it, on the outer parts, on the diaphysis of a long bone, you can see that there aren't very many air pockets. It's pretty much solid bone matrix and collagen. So that's where you have compact bone. And then spongy bone, you typically find it on the ends and also on the inside part of, again, you can see that this part right here in the medulla, you can see a little air pocket. So you also find spongy bone on the inner part of a long bone as well. And this is what we call the medullary cavity. So again, what confusing thing with cavities, we usually think of like cavities in our teeth, some sort of hole or puka in our teeth. We think nothing's there, but you do have something in the medullary cavity. It's just a space where something can be held. All right, so this is what compact bone looks like at the microscopic level. So as you can see here is that you have all these holes, and these are where blood vessels and nerves would run through. But the thing is that you also have all these little small pockets, and these are where the osteocytes would hang out in. So what we have here is all the blood would supply all these osteocytes, and what you can't really see at this magnification is that there are all these small little tubes and ridges that actually allow blood and other nutrients to diffuse from the blood and actually reach these osteocytes as well. This is what we call a compact or cortical bone. Again, so what we have here is that all these little concentric rings, these are something called osteons. So they're like very thick straws, or if you've ever been to like a print or copy center or a paper mill, you might have seen reels or reams of paper. And if you've ever been to like that, and don't do this in Kinko's and get kicked out, but if you ever like try to hit one of these or slap one of these, they're very thick, they're very hard, right? So same with compact and cortical bones. You have all these layers called lamellae, and they form all these concentric rings of bone tissue, bone matrix. And just like how these paper reels are very strong and very firm, same with these osteons. By building layers and layers of bone matrix, you form an osteon, and this is why compact and cortical bone is very, very strong. But again, why do you have those holes? You need something to supply and keep those cells alive in compact bone. Now, spongy bone, compared to that previous example, notice that you have a lot more of these air pockets. So this is also called cancellous bone or sometimes trabecular bone. These little like spikes or little bridges, these are called trabeculae. So what we have here is like compared to compact bone being forming those osteons, Now these are forming more networks, and you see a lot more of these spaces between these areas of bone right here. So again, you still have lamellae, but they're not forming those tightly wound and tightly packed reels like we saw with the osteons. All right, so again, remember compact bone is also called cortical bone, and spongy bone is also called cancellous bone or trabecular bone. And I know, like, some of you probably, I mean, it's not looking good for him. I think he's still alive, but I tried to come up with a mnemonic for this. So this is how I know trabecular bone is spongy bone. So here's Alex Trebek. If you don't know who he is, ask your mom or dad or grandpa. And this is the way you remember it. It was him holding a sponge. So trabecular bone is spongy bone. Compact bone is cortical bone. I haven't come up with a mnemonic for that yet. All right, so how do bones grow? So again, you have to go from that baby, and babies grow. So how do they grow? Well, they grow kind of like people. So the thing is that bones do lengthen, and there's two types of growth, or two directions of growth. Long bones can grow in length, and that's what we typically associate. But are you going to have the same thickness of bone as a child as you are as a fully formed adult? Well, it's going again, you grow in mass, you grow in size, you grow in height. So your bones also have to also thicken as well, just like a tree ends up thickening its trunk. So what happens is that appositional is what you call growth in width. So just like people, as we grow older, we grow not only in height, but unfortunately, a lot of us also grow width-wise as well. So appositional is width, and interstitial is what we call lengthening in terms of length. So again, this is what we typically think about when we think about bone growth. So they refer to different directions. So appositional thickening, width is, or appositional is thickening in width, but interstitial is referring to lengthening of a long bone along the long axis of a bone. So this is so this mnemonic I sometimes teach. It works for some people, but for some reason, it's not a very popular one. So width is appositional, interstitial is length, and thickness is appositional, and interstitial is length. So this mnemonic is called whale tail. Why? Because again, if it's width, you're growing wider. If it's interstitial, it grows longer. All right, so then again, the three terms referring to different parts of a bone. Long bone is the epiphysis, diaphysis, and the metaphysis. Now, what we're going to talk about is epiphyseal plates, or aka growth plates. So they're actually not quite at the metaphysis. They're actually at the border of the epiphysis and metaphysis. So what are growth plates? Well, they're involved in growth, and they're plates. So the plates something flat, right? So there's something flat that's involved in growth. So these are hyaline cartilage. So remember that you had that primary, or when you have endochondral ossification, you had that first center forming in the middle in the diaphysis, but you also had the bone forming at the very ends in the epiphyses. Well, you still have a little cartilage as you go from the middle, and where the two centers are meeting, you're going to have a little cartilage left over in the middle. So this is the site of new bone growth. So this involves endochondral ossification as well. So hyaline kind of forms like the scaffolding or the foundation or structure, or if you've ever seen someone or seen cement being poured, usually they lay down the wood to kind of hold the cement in place while it hardens. So hyaline is kind of like the wood scaffolding you use for pouring a new cement foundation. So human bones, they grow until about age 25. So I know now the thing is they grow until about age 25, but by that time they've already really slowed. Like when I was in college, I was like, oh, I'm 5'6", maybe I can grow a little more, but it never happened. Yeah, I know, it's you could get taller, but maybe a little bit, but yeah. Forget my dreams weren't coming true. I didn't end up becoming 5'9", so yeah. But technically, yeah, you grow until about age 25, but things have pretty much slowed down by then. But you're still growing. So yeah, by the time you're completely replaced, you're an adult and age 25, your cartilage is completely replaced, or not the ones at the very end, but the growth cartilage in your growth plates. That's pretty much all replaced by bone. So then you have something called the epiphyseal line. That's what remains after that. So again, remember, the cartilage is being constantly replaced by bone, and once that last bit of cartilage in the epiphyseal plate is replaced by bone, now you have a line of bone. And here's a hand. So here's a hand, but it's in a growing child. So remember, throw back all the way to x-rays and CT scans. So when you have an x-ray and CT scan, the denser an object in, the whiter it appears. But what are all these arrows pointing to? Well, notice that they're pointing to these areas right here. So you do see that kind of compact bone. Notice that it's very white and bright. So that means this bone is very dense. So you have a bone here and bone here, but what it's pointing to are these dark regions. So actually you have these bones forming, but this is all cartilage. It's not empty space, but cartilage is less dense than bone. So cartilage will appear as darker areas in a growing child's growth plates. So yeah, notice that these haven't quite fused. This is all cartilage where you have this little gap between the two bones right here, or two sites of ossification. Now here's an adult bone. So what we have here is that compared to the child's bones and the joints, same joint in this case, well, notice that you don't have that separation. So there's no longer cartilage here. Now it's completely formed compact bone over here. And actually you have these little lines. So it's kind of very faint, but compared to a darker region like this, now you have these little lines where these growth plates have being completely replaced by bones and bone tissue. And now you have these small little epiphyseal lines. So again, this is why it's very important in terms of children and growth, that they have cartilage, they're still growing, that cartilage is still being replaced by bone. So back to our question, should children lift weights? And I know I love that t-shirt, but this is why it's often like, I haven't gone to like bodybuilding.com, but I'm pretty sure that debate is still raging to today. So then, is it safe for children to weight train? Well, here's the thing. The things that growth plates, that's why I cover it. This is where it's very controversial. Like cartilage, strong, but not as strong as bone. And remember, bone is there for support and weight bearing. So what happens here is that you have the elite basketball players, and they're playing a lot of basketball, a lot of impact on these growth plates. But now they're saying like, okay, if you kind of damage these relatively fragile, they're still strong, but not as strong as bone. If you start damaging these growth plates, will that cause the ossification to happen kind of like in a awkward position and end up forming deformities? So growth plate vulnerability. So what's happening here? So what we see is that growth plate fractures. If you fracture that growth plate, there's no guarantee that will fuse together and that will grow properly. And another big concern is that if you injure growth plates, will that cause deformities or stunted growth? All right, so the thing is that, so will we have an answer to this question? Thing is that at least in the US, like it's really hard to do any studies on children where there's a potential harm to children. So yeah, it's the thing is that if we do have an answer to this question, it probably won't come from a United States-based researcher, because it's like, that's why a lot of things like drugs, like the doses they calculate for children aren't due to like, okay, let's give these child certain amounts of drugs and see at what point they start having ill effects. Usually it's due to some like body surface area or some sort of ratio based on adult values. So this is why we probably won't answer this question. Yeah. And let's see, actually there's some questions. So adults on osteoporosis, we might get to that if we have time. And then, cracking knuckles. When we get to joints, I might bring that up. But yeah, gas bubbles being released. Yeah, that's what they have. There's actually like small, tiny gas bubbles. There's a really cool, I wonder if I can find that x-ray. There was a really cool x-ray where they actually showed the bubble being formed. So it's something called cavitation. And knuckles. That's a really clever term, but you could kind of think of that. When you have some sort of like change in pressure and vibration, like all sound is some sort of vibration. So when you cause a vibration in the synovial fluid in your joint, and that's also vibrating the air. That causes the sound you hear when you crack things. You crack your knuckles. All right, so bone marrow. So again, even though they have that medullary cavity, does that mean your bones are just full of air? I mean, when you're dead, yeah, they end up full of air because you're left over with bone. All the cells have died, all the proteins have disintegrated, and you're left with mineral. But in your bones right now, is there just nothing but air? So actually, this is the head of a femur, and what you see is bone marrow. So again, even though we saw in the previous picture with the spongy bone, you had all those air pockets, that's in dead bone without any living cells or biodegradable tissue. But what we have here is red marrow. So these are actually cells and yellow marrow as well. So here we have the bone, and here we have the red marrow and yellow marrow. So bone marrow comes in two colors, red and yellow. Now yellow marrow, so there's I forgot the species, but there's these birds, and I think it was like in Africa. What they do is like they're scavengers, and then they take bones from dead animals, and they fly to very high heights, and they actually at high speeds drop these bones, and they use it to crack open these bones and extract the yellow marrow. So what other tissue in our body is very yellow or off-white and yellow? It's a connective tissue. Yes, adipose tissue. So that's what yellow marrow is. It has a lot of fat. So this is a characteristic of yellow marrow. And if you've had an Italian dish called ossobuco, this is basically a bone, you just cut it in half, and you have all this like fatty marrow on the inside. So yeah, this is why it's very rich and very oily, as you can see here. Or if you had that yummy tonkotsu ramen, which tonkotsu literally translated from Japanese means pig bones. So you also have all that. It's very tasty, very rich, but also very fatty because of all that yellow marrow as well. So this is why that vulture is like these birds of prey and raptors. They like cracking open those bones. You get all of that calorie-dense, nutritious yellow marrow. And that's why some people love this kind of like using bones or bone broth, because you have all those fats and triglycerides and all that richness you have from yellow marrow. And then red marrow. So this is source of hematopoietic stem cells, and so these are very powerful. Remember, stem cells, they not only can form, regenerate, and undergo mitosis, but they can undergo differentiation. So red marrow, these hematopoietic stem cells, have the potential to become any type of blood cell in your body. So they can become red blood cells, the many types of white blood cells, and also platelets as well. So that's what we have here. Yeah, and apologies if you're vegan, by the way. But yeah, this is just like, that's why I use the nature example. But where do you find red marrow? You find them in the flat bones and the spongy ends of long bones. So that's where you find that. And the thing about red marrow, you don't have red marrow forever. So the thing is that when you're very young, your bones are full of red marrow. But as we age, so it's kind of like bone growth. As we age, what happens to a lot of us? Speaking from experience, you start to accumulate adipose, right? So red marrow eventually becomes yellow marrow as we age. So here we have an infant. As you can see, this infant has a lot of red marrow and doesn't really have yellow marrow yet. But during childhood development, you start seeing yellow marrow start to form in the middle. And then adolescent, you can see the conversion from red marrow to yellow marrow. And by the time you're an adult, you have mostly yellow marrow. You still have red marrow there. So this is why if you've ever tried to do a bone marrow, actually I forgot to contact our bone marrow. So if you ever try to donate bone marrow, one question they always ask is, what's your age? But why is that? Well, thing is that the thing is that with bone marrow, well, as we lose red marrow with age, this is why by the time you have 45-year-old or above, they still have red marrow, but it becomes very hard to extract red marrow from someone who's an adult or like near their middle age. Versus the thing is that, yeah, you still have red marrow when you're a young adult. So this is why they try to recruit young adults. Again, you don't want to, have we learned nothing from BioShock? You don't harvest babies. So again, it's like, okay, so then infant, child, and adolescence, you don't want to harm growing up, developing bodies, right? But once you're a formed adult and you can handle a little, but actually now they don't really, they try not to do that actual extraction from the hip now. So actually what they try to do is collect something called peripheral blood stem cells. So you actually don't have to drill into someone's hip and extract the red marrow. So this is why, I mean, like I know some, my friend in San Francisco, he actually donated bone marrow, and I think he said it felt like he had done deadlifts for like max rep deadlifts for 3 straight days after he donated bone marrow. So it does hurt after a while, but now they actually try to collect it from blood, and instead of having to actually drill into the bone marrow and extract bone marrow from inside a bone. And let's see, bone diseases. So and actually we're kind of ahead, so I'm really happy we're kind of ahead. So bone diseases, well, hormones control bone growth. So things like thyroxine, a major form of thyroid hormones. There's actually multiple forms of thyroid hormones, but thyroxine is the one that has major effects on bone growth. And then you have growth hormones. So growth hormone is also involved not only like some people take it for like growing muscle tissue, but also causes bone tissue to grow as well. Or say, like I had a friend growing up in, I think, how old was he? Maybe 10 or 12, but he was below in the bottom quartile for growth. So they actually prescribed him human growth hormone so he could end up, yeah, so he was actually short, but now he's like the same height as me now as adults. And then both stimulate bone growth, and this is what can happen if you have too much. So here's gigantism, and here's acromegaly. So this is both the results of too much growth hormone. As you can see, this guy is really, really tall, right? But what do we have here? So acromegaly is not just about growing in terms of long bones, but this guy has something unflatteringly called, they say a classic symptom is lantern jaw. So his mandible actually widen as well and start elongating as well. And actually, oh, ignore that, don't worry. Okay, so what we have here, so this is normal bone on the left. What do we have here on the right? And someone did mention it. So is it more dense or less dense? Yeah, so B, as you can see, is less dense than A. So what's happening here is, so this is health bone, and here's what we see in osteoporosis. So when you have something that's porous, that means it has a lot of holes, it's very hollow, right? So osteo, remember referring bones. So now you're forming bigger pores. You're forming now this bone is becoming less dense and more porous. So what causes osteoporosis? Well, what's happening here? So we have well, again, what sex are these people right here? They're women, but what's happening to them? So what do you think they're experiencing? Combustion? Nope. But they're experiencing some sort of heat, right? Menopause. But what's one symptom of menopause associated with that heat? Hot flashes, right? So it was really funny. One year someone said, they're going Super Saiyan. No, they're not. But they're experiencing these hot flashes, and that's occurring due to menopause. And what age group is typically affected by menopause? Young women, older women. Yeah, so then menopause. So the thing is that estrogens and androgens, these are your primary sex hormones. But the thing is that estrogens and androgens, especially like estrogen, primary female sex hormone, or actually more specifically, estradiol. So the estradiol is something that promotes osteoblast activity. Now, osteoblasts, do they build bone or do they crush bone? Yep, I'm seeing the right answer. So remember, osteoblasts build bone. So if estrogens promote osteoblast activity, what do estrogens do to bone density? They help osteoblasts build more bone. Now, the thing is that they also not only promote osteoblast activity, they also inhibit osteoclast activity. So what happens is that by estrogens, they promote the builders and they hold back on the osteoclasts that crush bone. So overall effect of estrogen on bone tissue is that you increase bone density. But what happens with menopause? Well, a woman has finally ovulated her last egg. So what happens is that you don't have that menstrual cycle anymore. Without that menstrual cycle, you don't get those surges in estrogens and progesterone. So when you don't have those surges in estrogen, that means a woman, postmenopausal woman, their estrogen levels just tank. So if you have a drastic drop in estrogens, what happens? You don't have that as much osteoblast activity, and you don't have as much brakes on osteoclast activity. So now that imbalance starts to happen, you have less building, and now you have more reabsorption of calcium from bone and release of calcium from bone tissue. So yeah, so this is what happens when you have menopause. A drop in estrogens, less osteoblast activity, and now the osteoclasts start to dominate. So this is what happens here. If those osteoclasts now don't have the brakes on, and you don't have the osteoblasts to repair that bone, now you're going to have all these little holes forming. Why? Because again, that imbalance due to osteoblasts and osteoclasts due to that big drop in estrogens. And yes, so this is why women are typically more prone to osteoporosis. Does that mean men are totally immune to that? Well, there are less incidents, but again, the thing is that men also lose androgens with age too. So men can develop osteoporosis if they have low bone density, or if they don't watch their nutrition. And also, like, the thing about bone is it's very interesting. Like, if you stress bone, it actually builds up bone mineral. But if you have a woman or older woman or an older man, and they don't get out much and do a lot of physical activity, they are at increased risk of osteoporosis.